Welcome back to Particle Physics and the Standard Model. This is lecture 48, and in the last class we finally got done with all the nice bits about the Standard Model. We finally finished deconstructing the Standard Model. We ended by looking at confirmation of measurements of delta m squares in the neutrino sector, the confirmation of atmospheric neutrino and solar neutrino results in reactor neutrino results. Okay. And in particular we took the results from the Chu experiment in France, which measured the probability of retrieving an electron neutrino as an electron neutrino again after propagation, and they set bounds on the plane of delta m square and sin square 2 theta, which are the unknown Lagrangian parameters, right, Lagrangian derived parameters. And at various base lengths they did this experiment, they kept varying the base length, tried to measure the probability, and the result was that they were able to set a bound with the correct behavior that you expect that was consistent with the atmospheric and solar neutrino measurements. Okay. And then we looked at the names of some of the other experiments that do all sorts of neutrino oscillations. We talked a bit about the anomalies that they are seeing and why this is an exciting field, and finally we thought a bit about whether quarks actually oscillate or not. The short answer is no, because they immediately decohere by interacting with the environment. Okay. Any coherent superposition that you can write down of the flavor eigenstates would immediately decohere, okay, upon propagation. Because why? Because we are after all dealing with the strong interactions. So you have to first of all put them in confined bound states, and they get rapidly stopped in the medium. Okay. And then we turned over to a new chapter in our course, which is dealing with relativistic kinematics, okay, which will lead on to collider physics and all sorts of very interesting things. We warmed up by writing down Lorentz boosts and identified what was the Lorentz invariant here, which is literally the invariant mass. Okay. Now let us put this in the context of 2 to 2 collisions. What do we mean by that? Let us say I have, okay, now this is something like a Feynman diagram. Okay. So I have a particle P1 and a particle P2. You do not have to think of this as a Feynman diagram really, actually it is actually happening in real space. Okay. Nevertheless I am drawing a blob to indicate that some collision has happened there, some interaction has happened, and you get 2 outgoing particles with momenta P3 and P4. Okay. Now how do I write the momentum transfer here? I can either write it as P1 minus P3 or P4 minus P2, correct? Why is that? So I have just made use of momentum conservation. This is all for momentum conservation in fact. Okay. So everything here I am writing is not, this is all in 4 momentum, this is all 4 momentum, there is no 3 momenta here. Okay. Only when I put an arrow on top it stands for a 3 vector. Okay. So all I have done is just rewrite this, right. So P1 plus P2 is P3 plus P4, momentum conservation, 4 momentum conservation. This quantity is generally denoted by Q. Okay. In most collision processes you will notice that it is Q that is actually important, it is the momentum transfer that turns out to be the figure of merit. Okay. So let me as well write 4 momentum transfer so that it is clear, and if I have Q square larger than 0, right, is this a sensible, is this a reasonable thing to happen? Could scattering actually happen this way? Of course it can, okay, because in our metric this is time like, agreed. Our metric is what? 1 minus 1 minus 1 minus 1, yes. So, this is time like, so okay, and what is this? This is space like, yes. So, again I stand corrected, I meant space like is what we would actually want, okay. Time like is what does not happen, right. So, space like would mean this can accommodate a scattering process. Okay. So, think of the light cone Tx. So, this is time like, right. This region we do not it is unphysical, this is the region that works out, right. So, that is what I meant here in our metric especially, right. So, okay, this would this has when we say p square equals m squared, right, here we are assuming p square is positive, right. So, this is something like that, okay. This is like a particle mass, it is not exactly the mass here because this is a momentum transfer, okay. This is like a mass in the scattering problem, but this is really what should happen if you want a scattering to happen, q square should be less than 0. Okay. Now, let us ask if I want to create a particle in a collision. So, here I have just glossed over the fact that P1 and P2 they came together and then they actually created 2 other species, right, generically. So, that means one can ask how much energy was available to create those particles, right. If they came in almost at rest and then the final state particles happen to be much heavier, you are not going to create them, right, intuitively. So, we can try to quantify this, okay. Create particles in a collision, and let me draw one more picture to show this a bit more intuitively, okay. So, what I am drawing here is the initial state of the collision. A and B are 2 different species that are coming in. So, now you see I have drawn them coming in from slightly 2 different directions, right, because that is a bit more intuitive to what I want to say. Then I ask what is the total momentum, 4 momentum squared of course in this case in this initial state. What is that? That is nothing but the total energy of the initial state minus the total momentum of the initial state, but here I am talking about 3 momentum, that is why I am putting a vector sign. Okay. So, what is this? If I expand, I get a E squared minus PA squared, that is an MA squared, and then EB squared minus PB squared, that is an MB squared. Then I have all these other cross terms, right. So, I have 2 EA EB minus PA dot PB. Good. Let us give this equation a name, okay, because we are going to keep using this in this lecture. I am going to call this equation star, equation asterisk if you want, okay. Now, let us say I want to create a particle, okay, of mass m. In fact, I want to call it mass mc. Why? the particle that species I am going to call it C. Okay. Would you agree now that this would imply I want the initial momentum squared to be larger than mc squared, yes, larger than or equal to, right. So, that is my condition, and let us see how this condition is satisfied in various situations. Okay. Not only that, this applies to any number of particles in the final state, right. Such that their invariant mass, right, the final state invariant mass is, I can just call it the invariant mass squared, I can just call that m final squared. Okay. Basically all I am saying is the condition is that the invariant mass squared of the initial state should be greater than or equal to the invariant mass squared of the final state. This is just what P dot is, yeah, for momentum squared. Okay. So far so clear, right. Of course, we can give this an expression too, just to be clear. This is nothing but, if I have a number of particles labeled by I take the sum of the energies of those of the final state and square it, minus I take the momentum, 3 momentum of all the species in the final state, sum over it and square it. Okay. So, this is the condition in general. The fun is when we see when we actually look at specific situations in which this condition is applied. Okay. So, let us consider 2 configurations, the most popular configurations in which particles are created in laboratories called colliders. Okay. First, let us take a simple configuration called fixed target. What would that mean? Just means the target is stationary, sitting somewhere, and then you are throwing some beam at it. Okay. As simple as that, you are just throwing rocks. Okay. Throwing rocks at a wall, basically, that is a fixed target experiment. Okay. And in particular, we had A and B, right, over here. So, I am going to call B as the target, A as the projectile. Any experiment can be turned into a fixed target experiment. How? You just go to the rest frame of one of the colliding particles. So, in this case, this picture is in the lab frame A and B, what you are seeing here. If I go to the rest frame of B, then in that frame B is stationary, and so it is a fixed target experiment. A is a projectile now. Okay, that is all we are doing actually. That would imply that in my master formula, right, remember this is the master formula over here, the star equation. Let me just keep that around so that we can see what is going on. In that formula I set Pb to 0, and what is Eb? That is just the mass, the rest mass if you want. Okay. What would that imply for the invariant mass squared of the initial state, or P squared total? So, I am just going to import that from here. So, MA will remain MA, MB will remain MB, but EB is now MB and EA remains EA, whereas the PA dot PB term goes to 0. right, because Pb itself is 0. Yeah. Okay. Now what is the implication of that? Let us look at one particular case where your A is accelerated to such high speeds, okay, such high speeds that your EA is much larger than either mass in the problem. Okay. To give an example, let us take some proton beam which I am accelerating it to say 10 GeV, and then I am hitting protons on protons. So, MA is 1 GeV, MB is also 1 GeV, so I can neglect it basically. Basically in this problem it is as though the beam and the target particles are massless. Okay. So, that would imply I can neglect the first two terms, right. So, that I can write P square total as just MB times EA. Okay. So, let us keep this in mind. Okay, that is for fixed target. So, let me call that equation 1. Okay, because I want to compare this with yet another configuration which is a head on collision between the particles. Okay. Now, in this case I am going to make the lab frame the same as the center of momentum frame, or put differently I am just going to go to the center of momentum frame. Okay. Either way, however you want to think about it. Okay. So, I want to go to center of momentum frame. All that means is I am going to set PA equal to minus PB. Okay, that is all it means. Okay, in this case I have basically made the lab frame equal to the center of momentum frame in this picture basically. Okay. So, how do I think about this? Now, I just have to draw it this way, right. So, it is like A and B are coming in this way. So, over here B was just sitting around and then A was hitting it. Okay. Now, what happens if I plug this condition into the formula, the master formula star, then I get P tot squared equals, once again I have MA squared plus MB squared. Now, I have two EA, EB, I can do nothing about that, that is in my hands. Remember, this is not center of energy, center of momentum only. Okay, E and EB can still be fixed by you separately, they could be different. Okay. And this quantity, I am just going to call it the center of momentum, okay, PCM basically. What is that? PCM is nothing but either PA or PB, the absolute value of that. Okay. So, this is not terribly enlightening yet, but if we again go to this limit where the energy of the A beam is much larger than the mass of the A species, and similarly for EB is much larger than MB, in this limit what do I get? I can get rid of MA square and MB square, right. So, then I can say that P tot squared, okay, equals 2 EAEB plus PCM squared. Now, what is PCM squared here? Suppose we are talking about massless particles, that is what we have done here, right. We are literally taking mass to 0 compared to the energies, right. see it is like light scattering now, right. That would just mean PCM is equal to A and if I am considering the center of momentum frame, since the two momenta are equal, that would also mean the two energies are equal, right, and I might as well call it E. Okay. And this is always true in the massless limit. Yes, and in real life situations the two beams that you do collide, you do prepare at the same energy anyway, right. So, in other words, the equation I wanted to write was, in this case, it is just 4E squared. Agreed? E square from the first term, E square from the second term. So, that is a 2E square multiplied by 2. Okay. So, we are going to now compare situations 1 and 2. Okay. And before we do that, we are going to give a little more interpretation to this P tot squared to really understand what that is. Okay. So, we just said that is the initial state invariant mass squared, right. What is one other way to think about this? In the center of momentum frame, right, this is nothing but EA plus EB the whole squared in the center of momentum frame. Agreed? That is what it is, right. So, because why? Because if I take the you go back here, we started out here, this term basically has gone to 0, right, this term in the center of momentum frame, right. So, in any situation, whether it is fixed target or center of momentum head on collision, this P tot squared can always be thought of as the total energy available in the initial state squared, of course, in the center of momentum frame. Even if it is a fixed target, you can always shift to the center of momentum frame. You can always boost to that frame and think of this as the total energy available in that frame, right. And that is the energy that you need to put in that frame, of course, in order to create the particles that you want. Okay. So, this gives us some physical meaning for how much energy we need to actually put in the process, how much energy needs to be there in order to create the final state particles. Okay. Now, in that light, I am going to rewrite 1 and 2, the equations 1 and 2, that tells me that the total energy in the center of momentum frame is, so I am now taking square root of all those equations, okay, would be 2E, see 4E squares, the square root of that is just 2E for head on collision, and what was it for fixed target? So, it was 2 MBEA, right, but now I am taking the square root of that for a fixed target collision. Okay. Now, in real life colliders, if you want to discover, okay, a heavy new particle species, okay, which configuration would you pick over here by looking at this? I would pick the head on collision configuration. I would pick using a detector where I have beams on both sides and I collide them head on. Okay, that is what I meant by you make the lab frame equal to the center of momentum frame in your configuration itself. Okay. Why? Because clearly if I have E much larger than MB, right, then which of these is bigger? Clearly this is bigger, right, 2E is much larger than that. Agreed? So, if you do not believe me, square this. Okay. So, if you square this, what happens? I get 4E square much larger than 2MBE again. So, that just gives me 2E much larger than MB. So, this is what I began with. So, as long as I have energetic beams, might as well build 2 energetic beams and collide them head on, and I am going to get a lot more energy in the center of momentum frame, so that I can discover heavy new particles. Okay. So, let me map that onto this. That is the advantage of using a collider with head on collisions of beams. Okay. Then what would ever be the advantage of using a fixed target experiment? Okay. That is, if you want to, so this is to discover heavy new particles, this is to produce many light particles, because if you do not care about going to higher energies, okay, by light particles I mean pions, neutrinos, muons and so on. Okay. We talked about all these neutrino beams for neutrino oscillations and all that, right. Where did they come from? You use fixed target experiments like these, okay, to study them, to study the decay products, oscillations and so on, because they are basically cheaper. You do not need to invest in 2 different beams, you just need one beam, some target, okay. So, they are more efficient and you can produce a lot of particles this way. Okay. You do not need to build a proper large circular collider. So, over here this configuration is exactly what corresponds to, let me call it a colliding beam accelerator. You need to accelerate them to very high energies, right. So, sometimes just call collider. To me both are colliders, but people generally use the word collider for more commonly use the word collider for the first configuration, okay, head on collisions. All right. So, let me wrap up this lecture by giving a couple of names for these 2 configurations. The efforts that people put in to build this kind of stuff, it is known as the energy frontier in particle physics or collider physics. Why? You build 2 beams with higher and higher energies, you prepare 2 beams with higher and higher energies, and you are basically increasing the energy reach of particle physics by going to higher energies and trying to produce newer and newer particles, right. So, that is the energy frontier. This one is called the intensity frontier. Why is that? Because here you can produce a lot more particles, you cannot produce newer particles, okay, not generally, but since you have a beam you can run it for a very long time and you just produce many more pions and neutrinos and whatever hadronic showers. So, that gives you a lot of statistics to deal with. Basically here you are talking about intense beams, okay. So, one comes at the cost of another. So, both are equally important to push the frontiers of particle physics, okay. So, I will leave you here, and in the next lecture we will take up some examples of these frontiers and move on to cross sections, decay rates and things like that. All right. Okay, I leave you here. Thank you. See you in the next class.